Hi there, this is Jacob Nash, and this is a review of Unit 2 for AP Statistics. So, we have two different kinds of variables that we look at, and you might usually think independent variable and dependent variable. Well, just so you know, we can also say explanatory and response. It kind of makes sense because this is the cause. Well, got to be careful that if you're talking about a correlation, then that does not show causation. That's something very important. But usually the independent variable is something that causes something. It explains why, and then the response to that. So the independent variable, what you're changing is the x. The x changes, and in response, we get y, which can be high or low. So the next thing is when we're looking at a scatter plot, so this is about scatter plots. There's four things that we have to say when we're interpreting a scatter plot. So first of all, if you don't remember what that is, you could just have like, okay, that didn't work. You can just have like dots. All right, that's just great. Let's try this. All right, that's just great. Okay, new thing. So scatter plot, it could just have dots, that, and then you might want to make a line of best fit, or as we call least squares regression line, to fit that data. But whenever you are talking about it, the first thing you need to know is it positive or is it a negative correlation? Well, in this case, that's a positive. A negative is if it's like this. The dots go like this instead. Just like how when you look at slope. Now we can say things like strong and weak. We need to say that, and there could be moderately too. Moderately strong, moderately weak. But this, I would say, and how do you determine if something's strong or weak? You might think it's by how steep it is. Well, it can be, but it can you have to know that it can also be how close the dots are to each other. When I do something like this, that suddenly makes it weaker, right? And so you need to say that. These are things that you have to do or you won't get full credit. All right, the third thing that you need to do is you need to identify that different variables, your x and y, or you could explanatory response, whatever. And that would be just on the axes of whatever your problem you're given. You have to say that. The last thing you need to say is if it's a linear correlation. So you would need to say, for this one, for example, you would say, this is a positive, strong correlation between whatever there happen to be, and it is linear. If it's not linear, then that we might have a problem. But anyways, there you go. The next thing that we need to know is R. What is R? R is the correlational coefficient. So I'll just say co, so I don't have to write that whole thing out. Correlational coefficient, what does that mean? Well, it ranges on a scale of -1 to 1, sorry. -1 to 1. As you get over here, this is strong. 0 is weak correlation. And then 1 is strong once again. So as you get closer to -1 or 1, it's strong. And as you get closer to 0, it's weak. We can mostly say that from 0.7 or -0.7 to, in this range, see, is there some kind of like highlighter thing? I don't know, spray paint, maybe that would work. So in this range right here, pretty much, I don't know, that's kind of tacky. Sorry about that. That is what we would consider strong. And then pretty much in the middle of that, maybe like 0.4 to 0.7, that's moderate, a moderate thing, and then this is just flat out weak in these areas. So that, and just so you know, here's what it would look like if it was strong, or if it was negative strong, it wouldn't look like that. It would look like that. The points are close together, like that, and they show like they're all doing the same thing. Over here, moderate would probably be something like, I don't know, like that. This would be moderate, and then weak is just like, oh, all over the place. And then 0, that would literally be if they were just like nothing. So that's correlational coefficient, or R. The next thing that you would want to know is, oh, sorry, least squares regression line, LSLR. What is this? This is a line of best fit. But we just call this in statistics. And why would you use that? Well, we usually use this in scatter plots to kind of just make a line that best fits the data. Usually that would mean that there's same amount above or same amount below. If you want to make a least squares regression line, then what you have to do is you first need to think about if it's straight enough. If it's not, then you would want to do a transformation first, which we'll talk about. But in this case, this would be fine. And we're going to get into more detail. But basically, if you want, how do you find this? Well, there's lots of things you can do in the calculators. But you can plug your values into L1 and L2 and then do 1-bar stats. And this line is like this. It's y hat. We have to use that because it's not the real y. So make sure you have y hat equals a plus bx. All right? And this is the same thing pretty much as y equals mx plus b, but we just have to use it in this way in statistics. So we don't use that one in this. So obviously, this is a different order pretty much, but b is the same thing as m, which is the slope. And then this a is the y-intercept. So in case you forgot what that was, the y-intercept is just where it hits the graph. So the y-intercept here would be somewhere negative or something. And then the slope is just rise over run, y over x, changing y over changing x. So the bigger the b, then the more it's going to be like steep. So in case you forgot that. So that's simply what this is. Something that you might want to know is how to solve for b and a. They might be nice and give it to you, but they might not. And here's how. So if you wanted to find b, well, I did just say it was rise over run, right? Well, we would have to multiply that by the correlational coefficient, r. And not just any y and x. It has to be the standard deviation of the y values and standard deviation of the x values. That's how we find slope for the LSRL. And then to find a, what we have to do is y. What does that mean? That the line over something like that, it means it's the mean. So we have to do the mean of the y values minus O. So you would have to know b first anyways, and then times the mean of the x values. So not that hard really. The next thing that you would want to know is residuals. What is a residual? Residual simply is just the actual y minus the predicted y. So a good way to remember this is A for actual. A comes first in the alphabet, right? So what does this really mean? It's how wrong were we, basically. So here's what I mean by that. So let's go back. Let's just say this is our scatter plot, okay? And then we just make this our least squares regression line, okay? Well, let's say we wanted to find the residual for this point, okay? That would be the distance from here to here. So this is our predicted y, this is our actual y. And whatever this distance is here, and look, that would be the same for all of these. Just a straight perpendicular thing. That tells us how accurate we were, pretty much. And so if a residual is positive, that means that we underpredicted. And if it's negative, we overpredicted. So that might seem backwards. Well, think about it. If it's actual minus predicted, if we predicted something small, then it would be a positive value. So that means we underpredicted it. If we predicted something that was really big, bigger than the actual thing, then it would end up making it negative. Hopefully that makes sense. But it's not that really good, or whatever you want to say. It's not, we can't see that much just by looking right here. If you see like how we're trying to find a residual. So there's something we can do called a residual plot, where we just take this line right here, our least squares regression line, and we just make it flat instead. And then we get the points, the same points. So it's really just like turning this down, like making that knock down. This is a residual plot, and that is something that helps us better see if it was a good least squares regression line. So how do we know if it was? Okay, so let's say, all right, this is our residual plot. We are looking for no pattern. No pattern. If we see a pattern, then that means that's a trash can least squares regression line. So if we have something like this, that's good. That's not a pattern, because they're kind of just like, oh, all over the place. But how about this? Let's say we have like that. Oh, well, that's not so good, right? That kind of looks like a pattern. And that's not the only thing that we can do. We can also look at something called R squared, the coefficient of determination. And if you realize, that's just the correlational coefficient squared. We get a decimal when we have this. Let's say it was 0.8 or something. Well, that means 80%, right? If that's a percent. And it's saying 80% of the variation is explained by that. So basically it means that that line is good for 80% of the data. So obviously the higher the R squared is, the better. If we have a super low R squared, then that's a trash can line. But what do we do with the trash can lines? When we have a trash can line, we can do something called a transformation. Whenever we're doing a transformation, we're doing something to the X or the Y. Well, I don't know, I just wrote that backwards. Usually the Y, you can do things to the X, but we usually do things to the Y to make it be linear. So let's say this was our residual plot. Okay. That's a pattern, isn't it? Since that's a pattern, that is not good. But if we take a step back and we're actually looking at the real graph, so X, Y, okay? Let's say we had that once again, all right? All right, we have something like that, and then we decide, okay, we're going to make our least squares regression line like that. Then the residual plot would look like this. That's bad, right? So we got to do something about that, because obviously, if you can tell, that doesn't really look like a linear relationship. Let's say this goes through 0, 0. So what does this look like? You might think it kind of looks like exponential. Well, if it goes through 0, 0, it couldn't be exponential. So that's how you can tell. So we know this is a quadratic. If we saw more, we would see that it's like that. If it actually was exponential, then it would look more like this. It kind of starts out slower. So we got to figure out what's the problem. All right, we should have this, shouldn't we? What's the problem? The problem is that the y's went too crazy. They went too high, right? All right, so this is a quadratic. What does a quadratic have? A quadratic has something squared, right? What's the opposite of that? Anytime we're doing a transformation, we'll have to do the opposite. Square root. Okay, well, let's say you thought, okay, let's square root the x. That would just make it like that. That's not so good. Because the problem's not that the problem is either that the x's are too low or the y's are too high, right? Because the x's, they're like, okay, come on, hurry up, because we should be over there, right? Or you could say, oh, slow down, y's, we should only be right here, whatever. So that's not a good idea. If we square root the x, that's going to make it even worse, like 2 times as worse. So we would need to square root the y. Then that would make it like that. Another thing we could do is square the x, because like I said, the x is too low. But, usually I would recommend doing something to the y. So let's just do that. Then, there you go. The transformation made it better. That's not the only thing that you can have, though. Usually the only other possible thing is if we had an exponential, like I said, all right? What's the problem here, okay? Problem is, once again, that the y's are too high or the x's are too low. But since it's exponential, we know that can be something to the x or whatever. And then the opposite of exponential is log, isn't it? So we could do log y to fix it, and then it would be like that. Because we always have to do the opposite thing. Like I said, I would recommend doing something to the y, but if you want to do something to the x, we could actually do 10 to the x, but like I said, it's probably better just to do log of y. All right. Now, there's also opposite things. So let's say we had this. All right, well, now we have the opposite problem, all right? So this goes through 0, so it's got to be a square root thing. Well, this time the y's are too low, right? So instead, this time we could square the y, because we know this is a square root function, so we got to do the opposite, which is squaring. All right, and then last possible thing is you could have a logarithmic thing. So hopefully this calculator pulls up. Let me remind you what that looks like. Okay, so let's just do, okay, that's crazy. I don't know why that's in there. All right, let's just do log x to remind ourselves, what does that kind of graph look like? Ignore that box plot. So it's like that. It doesn't even, it's like this. So it kind of looks like the square root. So you can't get confused. Since it's right here and it doesn't go through the origin, that's how we know. It's back to algebra, remember? It's got to be there. And if it was the exponential, then it's 0, 1. But anyways, so if we saw this, we would know, okay, this is a log thing. And it's making the y's too low, so we got to do 10 to the y. In this case, though, I think it might be easier to do log of x, because that 10 to that's a little bit kind of crazy to do. But in all the other situations, I would use y. But that's transformations. Something else is extrapolation. All right. This is a bad thing. So thumbs down. Bad. Well, that kind of looks like a knife. All right. I'll just do X. Bad to do. And what does it mean? So let's say you were trying to study like the weight of a child 15 to 20 weeks after it being born. So let's say that was like, okay, August, or I'll just write the numbers. So let's say it was like August 1st, 2003 to, what would 5 weeks later be? All right, 8, 15, 22, 29. Let's just change this. Okay, wait. 30, 1, 2, 3, 4, 5. 5. Oh, okay. I don't know. That might be wrong. August. Okay, that's right. All right, there you go. That's dumb. There's no point in the dates. But anyways, if someone was trying to study, let's say on 9/6 or on 7/31, that's extrapolation. Bad, because you cannot assume something that we might be studying a correlation. Doesn't mean causation, does it? That's something you got to know. You can't say by looking at a scatter plot, you can't say that means that causes that. You can't. You can only do that with an experiment, but it's statistics, right? No experiments for us. So you can't say that it causes that. But and so if you did try to assume something like a day out of that range, that's why extrapolation, whatever, however you want to say it, that's why it's bad, because you're trying to say, oh, I guess I can just follow the same pattern and just assume that that's what it's going to be like. And yeah, this thing's kind of messing up a little bit. All right, the last thing that we're going to want to know how to do is it could say, what is the blank form of something? So you have to change the form. It kind of is like a transformation, but you literally have to do it. So let's start out with this. All right, we have the square root of y equals y hat equals, let's just do simple numbers for now, all right? And it's saying, oh, what's the squared version? Okay, well, we got to figure that out. We have to get y by itself. How is that we do this? But we have to do it to both sides. Fortunately, you don't actually have to do anything to the numbers. You can just leave it like that. But we know if we were in like an algebra class, they would probably tell us to, but we don't have to, luckily. And then the other one that's probably not as straightforward to you is this. If you had log of y hat equals this. All right, now what do? You might say, what's the opposite of log? Exponential, but we just have to use our common thing that we should know, hopefully, that's this. A to the c power equals b is the same as log base a of b equals c. So that just tells us what things to do. All right, so if we're trying to change this to exponential, all right, b is y hat, see, because it's right here. So we know that's going to be on the other side by itself, which is what we want, right? Because we're trying to get y by itself. So we can just go ahead and do that, right? We don't need to put it on the right side. We'll just put it on the left side. And then c is going to be whatever was on the thing by itself for the log, which is this. So we know it's going to be to the power like this. That's going to be the exponent. But now, question is, what's a? What's going to be our thing down there? It's whatever the base was. There's no base there, but it's really 10. Hopefully you know that. That's why earlier when I was saying you would do 10 to the y, 10 to the x. All right. Sometimes you might need to expand this out. And remember, if you know your exponent rules, we have to do this. See, we can separate them, but if we do, we have to multiply the two things. That's what we have to do. And so then you could do 10 to the 9, and then I don't know if that's really necessary, but I guess just to show you what it would be like, we can do that. It's usually going to be smaller numbers than that, probably. So that is 1 billion, right? Just trying to write these zeros close to each other, right? And then it'd be times, and then we got 10 to the third, 1,000 to the x. And there you go. Now it's in the common like algebraic exponential thing that we usually think of. So that's the last thing. That's it for this unit. That's all.